70? Sure hope so. Okay. So 70 says, give or find a possible vector line equation in the IB component form for a line that intersects the following 2 points. So we have these 2 points. So in order to do that, what I'm going to do is I'm going to first pick one of the 2 points. So I'm just, for the sake of argument, I'll pick the first one. And then I'm going to calculate a slope. And it doesn't matter the order in which you do the subtraction. Which one is the y1 or x1, y1, or the x2, y2? So there's that. So this point is going to turn into my point vector. And this slope is going to turn into my direction vector. So my vector equation for a line then is this. And there's 4 versions that you could have written of this, depending on whether you picked 6, 1 as the point, or -4, -1 as the point. And then whether you used the slope as 1/5, or you did the slope as -1 over -5. So those are the 4 possibilities. Any combination of those would be fine, though. So your answer might not match that one exactly, but if it's the other point, or if the 1 and the 5 are both negative, that's okay. Any combination, that is fine. Anybody else with questions? Lucas, right? Yes. 62? 63, okay. So 63 says, find the slope-intercept form for the following lines given as vector equations. Okay. So what I'm going to do is I need to get a point and a slope out of this vector equation. So the point I'm going to pull out is going to be the point 4, -1. And the slope that I'm going to pull out is going to be the y over x. So I'm going to write that because I'm writing 2 over 2 here. I don't want you to be confused that it's which one is over which. So make sure that when you do that, you're taking the y coordinate over the x coordinate. Or in this case, really just 1. And then I can just take y equals mx plus b and plug things in. So -1 is equal to 1 times 4 plus b. So b is -5, or y equals x minus 5. Is that cool there, Lucas? Yeah. So again, the trickiest part is just getting the information out of that vector line equation, and then it turns into like an Algebra 1 problem. Anna. Sure. So 57 says, determine whether the given point lies on the line. And the tricky part for this is probably that, that they gave us the what's this called? The linear combination form instead of the IB component form, right? That's what we're probably having trouble with. I'm assuming you're able to do the ones before it that were in IB component form. So my plan here is I'm just going to translate this into an IB component form equation, and then it will be pretty easy to do from there. Does that sound okay? All right. So to do that, I'm going to start by distributing the I and j through. And then I'm going to group the stuff that has the t together and the stuff without the t together. Okay with that? Now I can translate these into component or IB component form because the I coefficient is the x coordinate and the j coefficient is the y coordinate. So that just becomes the point 1, 3, or the vector 1, 3, and that becomes the vector negative 4, 7. And so now I just need to check to see if negative 10, 17 lies on that vector or that line. And I can do that the same way I would have on 56 and 50, or 55 and 56. So I just create a system of two equations where the x components have to add to give you the 10 or the negative 10, and the y components have to add to give you the negative or the positive 17. So when I do that, I get 11 over 4 for t. And when I do this one, I get, what do I get? 14 over 7 for t. And since those are not equal, I know that point doesn't lie on the line. Does that feel okay there? Just real quick, check that. Yeah, okay, so that doesn't work. Okay. Julia. 76? Sure. Okay, it says find the intersection of the two lines if it exists. So just as a reminder, if we think back to our Algebra 3-4 class, and we're thinking about the intersection of two lines, there's 4 situations that we could run into, right? I'm sorry, 3 situations that we could run into. The lines intersect at exactly one point. They're parallel and they never intersect, or they could be coinciding and intersect everywhere, right? Those are the 3 possibilities for 2 lines. So basically what I'm going to do is I'm going to check first to see if they're parallel. And if they are parallel, then I have to tell whether they're going to be like parallel not touching or just coinciding. So I'm going to check to see if the direction is the same. And that'll allow me to tell whether they're going to be parallel or coinciding after that. Or if they're not parallel, then I can set them equal to each other and find the single point that they'll intersect at. Does that feel okay, Julia? Okay. So to tell if they're parallel, what I need to do is I need to take either this piece or that piece and set it equal to the other direction vector. So I can do that, or I could say this and solve for the variable. I'm going to just do this one here. So when I do that, s is -1/2, and I do this one, s is -1/2. So yes, they are parallel. Okay with that? So since I know that R1 is parallel to R2, I need to check if they're coinciding. So if they're coinciding, if I can find a point on R1 and that point is also on R2 or vice versa, I know that they're really the same line. If they're parallel and they share one point, they're going to share all the points. So I'm just going to take a point from R1 and see if it's on R2. So the point from R1 I'm going to use is 6, 9, because I know that's on R1. And I'm going to see if that is also on R2. So 2, 11, actually I have the problem over here. -4, -1, t. Okay, so again, I'll set up my system of equations where I have the x components have to equal 6 and the y components have to equal 9. So if I do that, I get t is equal to -1. If I do that one, I get, right? Yeah. And I subtract that. So this one I get t is equal to 2. So they're not coinciding. So there must be no intersection. On those ones. Let's double check that. This was 76. Yep, there is no intersection. So if you had jumped straight to setting the two equations equal to each other, you probably got a system that had no solution, right? Yeah, it gave you a line that there was like a 0, like a row of all zeros and then a 1 in one of the columns, right? In that column. That's telling you there's no solution, that basically 0 is equal to 1. Which I guess is going to coincide to, or correspond to this parallel not intersecting situation. But we have to be a little bit careful since we don't know if there's an intersection or not. The phrase that if the intersection exists was the part that made me suspicious and wanted to take a little bit more, be a little bit more careful than just setting the two equal to each other like we had done in the example where it said to just find the intersection, which kind of implied directionally that there was going to be an intersection. Here, because of that extra, if it exists, I wanted to be careful and make sure that what I was finding was, I checked to see first if there's like a no solution situation before I did that. Is that okay? Why all of a sudden the procedure changed there? Okay. And that's an important distinction, right? Ben.
Number 58, negative 5 the denominator.
Yeah, so it's the same idea as let me go up here to, oops, which one did we do like this already? We did 57, right? So on 58, we have r is equal to -5t plus -8 plus 4tj. So skipping all the way down to getting this in matched together, I have 0i minus 8j, that's the part without the t's, plus -5i plus 4j, the part with the t. So that gives me 0, -8, plus -5, 4. And then from there, I guess I'm hoping you're good. Okay. So it just means that it doesn't mean that there's a 1 somewhere. It means there's a 0 as the other component, but you have to make sure you're like pairing the stuff up the right way. You know what I mean, Ben? You're welcome. Okay. We ready to start this last section, this 8.8? All right. So in 8.8, there's actually, what we're going to be looking at is the 3D intersection of lines. And in that regard, there's actually 4 possibilities in 3 dimensions. So in 2 dimensions, we had 3 possibilities, right? We just mentioned this a moment ago. They can intersect 1 time, no times, or infinitely many times, right? Everybody's okay with that? In 3 dimensions, you can still have like parallel in the same plane. You can have intersecting, and that intersection means that like there is a plane that contains both lines in a single intersection. You can have coinciding still, and then you can have non-intersecting, non-parallel. So a situation like this, if my fingers are the lines, those lines are not intersecting, but they're also not parallel either because they have a different direction, right? This direction is this way and this direction is that way. Do you guys kind of see that? So what I've done here is I've written out kind of like a flow chart to kind of sift through this. If we're given 2 vector equations for a line, what do we want to check first, and how do we check it? So the first thing you'd want to do is check to see if the 2 lines are parallel. To do that, you take the direction component of one and see if it's equal to the direction vector of the other. And it doesn't matter which one you do. So again, the 2 lines that I'm basing this on are these 2 up here. Oh my goodness. Right, so in the flow chart where you're seeing R1, R2, or V1, V2, those are, or S or T or whatever, that's what I'm basing those on. Is everybody okay there? And we did just an example of that in 2 dimensions just a moment ago, right? So if the 2 lines are parallel, then we have to tell the difference between whether they're 3D parallel or they're 1D parallel or coinciding, right? Oh, I'm sorry, if they're parallel, they're only like, either they're parallel, non-intersecting parallel, or they're coinciding. So to do that, we want to check, does R1 overlap R2? And the way you do that is you take the point vector from either equation and set it equal to, or plug it into the other equation and see if you can solve for the S or the T. If that works, then the 2 vectors are overlapping, and if it doesn't, we say they're parallel. Now, if the 2 lines are not parallel, what we have to check to see if one of them intersects the other. So to do that, you set the 2 vector equations equal to each other and solve that system. That's the place where we're going to use a matrix and do that RREF thing. If that has a solution, then we know that there's an intersection. If we get anything else, then we know that there's no solution to that, and that they are that 3D parallel where they're, non-parallel and non-intersecting. So I wrote this out for you guys so it's a little bit clearer kind of what to do when and how we're going to do this, because a lot of the little tests that I'm doing to check for these things look very similar on a sheet of paper when I'm just burning through an example. So I wanted to kind of give you like a visual on kind of the process that I'm using and what I'm doing and when I'm doing it. And usually that helps students, at least the first time, as we're able to kind of track through and follow what to do when. You know what I mean, guys? So I'll give you guys a minute. I still see people writing, and then we'll do some specific numeric examples where we use this. Jacob.
Oh, what does it say? Like under yes, it like does R, then like I can't see the second part.
So I have, does R1 overlap R2?
Oh, all right, thank you.
And then on the other side it says, does R1 intersect R2?
All right.
Yeah, no problem. Am I cool to scroll and start some examples here? I don't want to cut anybody off because, again, this is important information, but it's also in the content library. If you're like, yo, I don't know that I wrote this down right, you can always go back there and check. So let's say we have R1. And then I have my R2. So we're going to determine the relationship between these two. If they're intersecting, we're going to give the point of intersection. So the first thing we're going to do is check to see if they're parallel. So I'm going to take the direction component of one and see if it's equal to the direction component of the other one, or the direction vector for the other one. And that's easy to see, right? We can do that by inspection. I can see that if t is negative 1/4, that definitely holds. So I'm not even going to bother writing the system out and like any of that. It's easy to see right away that one of the direction vectors is like a scalar multiple of the other. You guys see that? So again, you could write that out and do the solving or whatever and show that they all give the same solution for t. Or you can note that just whatever this value for t is that makes that true and just move about your business. But 4 times 1/4 is negative 1, or 4 times negative 1/4 is negative 1. Negative 12 times 1/4 is positive 3. 16 times negative 1/4 is negative 4. Right? Okay, so we know they're parallel. And then we want to check if they are overlapping. So I'm going to take the point vector from one and set it to the equation for the other. And it doesn't matter which one you do, whether you use the point vector from R1 or R2, but then it has to be set equal to the opposite equation, right? So 2 equals 3 minus s, 3 equals 0 plus 3s, and 3 equals 7 minus 4s. Hopefully it's easy to see there that s has got to equal 1 in all three cases. Everybody okay with that? So what that tells me is that that point 233 lies on R2. And since that point is obviously also on R1, and R1 and R2 are parallel, they have to be coinciding lines. They just have to be the same line. Ben? That is the point vector from R1 plugged into R2. So what I'm doing is I'm checking, is there a point on R1 that is also on R2? Then obviously we can get that point from R2, right? Yep. So all I would have to do in that case is set s equal to 1, and R1 is going to give me that point, or that R2 is going to give me that point from R1. And since the lines are parallel, they have the same direction and contain the same point. They must just be the same line. You're welcome. So we know those two lines are coinciding then. Does that feel okay with what we did there, guys? Okay. So the hardest thing here is just kind of keeping track of the little tests and what they mean, right? Because they feel, when I set them up, they feel similar. But looking at that flow chart, and I wrote out the equations that I'm using carefully, so if you're careful about that, it shouldn't be too bad. But let's So there's my R1 and R2. So the first thing we'll do is check to see if they're parallel. So I'll take 4, 5, negative 3 times t and see if that'll equal negative 6, negative 9, positive 2. So I can see 4t equals negative 6 should be t equals negative 3 over 2. 5t equal to negative 9 should give me t equals negative 9/5. Since those two are not equal, I know that they are not parallel. And I'm going to stop there because I don't care what the third component value for t would need to be. I can stop immediately. Everybody cool with that? So I know they're not parallel. So now I have to check, does R1 intersect R2? To do that, I'm going to set R1 equal to R2. and I'm going to turn this into systems of equations. And if I rearrange things so I have the S and T on one side and the constant on the other, I'm left with that system. Now, how many variables do I have in this system? I have two, right? I have S and T. How many equations do I need to solve in a variable with, or a system with two variables? Just two. How many equations do I have? Three. Does it matter what I pick? No, but we do have to make sure that we check our answer that we get in the third equation. So we're going to solve that system, but we do need to make sure we go back and check to make sure that the solution to that system we're solving does satisfy that third equation still. Everybody okay with that idea? So this is one of the tricky things to remember. So I'm going to solve this system using a matrix. You can solve it by hand if you want to. That's not a big deal. But I like using the matrix because I can just type it into my calculator. So that's the matrix that I'm going to type in. So I'm going to do the RREF function on the 2 by 3 matrix, 6, 4, -4, 9, 5, -8. 2 by 3, 6, 4, -4, 9, 5, -8. Okay. Once I have that typed in, I'm going to exit out to the main menu, go back to the matrix menu, over to the math tab, and then scroll till I find the RREF function. And then I'm going to go back in the matrix menu and retrieve that matrix A that I just built and press enter. So what this tells me is that S is -2 and that T is +2. So I take a quick moment here to make sure that that checks out in equation 3, and it does. Oops. +4. Everybody's okay there. So what that tells me is that they are intersecting. And to find the intersection then, I can take either S or T and plug it back into the corresponding equation. So I'm going to take equation R1 and plug T equals 2 into it, since that's R1 was the equation with the T in it. So I'm going to get 10, 14, negative 2. Oh, sorry, not negative 2, negative 5. So my point then is there. What do you guys think? You ready to do some practice with this? As you've seen me do a couple. This is the end of section 8.8 though. So those are the examples that were in the lessons. We still have over 30 minutes or close to 40 minutes here left in class, right? What I'd like for you guys to do while we're here is 119 to 122. You're doing exactly this, where you're determining whether the lines are intersecting, parallel, non-parallel, non-overlapping, or coinciding. Since we have 40 minutes here, let's try working on these here in class. And if you run into places where you're stuck, or you're not sure what to do, or you've got a result and you are kind of confused and you don't feel like very good about it, that we have a chance to kind of, you can ask some questions and go over some stuff. And, if you're not sharp on the calculator part, doing the matrix stuff, you can get all of that kind of looked at. And this will eventually be part of the problem set. So, like doing it now just removes maybe the hardest problems from the problem set having to do later. You know what I mean, guys? So I'm going to put up I'm going to go and put those 4 problems here on the board while you guys are working, so you can, if you don't want to have your tablet open because you have a lot of stuff going on your desk or whatever. Some of us like doing it on paper or whatever, so I'm going to put them up here for you if you need to look at them. Or so you don't have to look at them on your tablet, because I know that sharing screens and all this, the tablet screen just isn't really big enough a lot of time. Anyways, is that okay? So I'm just going to be kind of hanging out at my desk. If you need anything, or you have questions about anything, or you want to show me what you've done, or you've gotten to a point and you're not sure what to do, or you're just kind of generally confused about something, feel free to ask. Come on up, and I'd be happy to look at what you've done or walk you through what to do or any of that kind of stuff, okay? Does this feel good? I think it's nice to have some time to work on what are clearly the most difficult problems or most involved problems, let me put it that way, in the chapter in this kind of a setting where you're going to get to see some examples and then a chance to work on them straight away. Okay.